Hello students. This week, as you study the graphs of rational functions, you will encounter the concept of asymptotes. There are vertical, horizontal, and slant or oblique asymptotes. But what is an asymptote? The line x equals a is a vertical asymptote of the graph of f whenever f of x approaches infinity or f of x approaches minus infinity as x approaches a either from the right or the left. If you notice the graph on the left, this is the graph of the function f of x equals 1 over x. The y-axis, whose equation would be x equals 0, is a vertical asymptote of this graph. As x approaches 0 from the right, f of x is approaching infinity. And as x approaches 0 from the left, f of x is approaching minus infinity. The line y equals b is a horizontal asymptote of the graph of f whenever f of x approaches b as x approaches either infinity or minus infinity. In this graph on the left, the x-axis, whose equation would be y equals 0, is a horizontal asymptote of the graph. Notice that f of x is approaching 0 as x approaches infinity, and f of x is also approaching 0 as x approaches minus infinity. As another example, look at the graph on the right. This is the graph of f of x is 2x over x squared minus 1. Here we have two vertical asymptotes, x equals minus 1, this dotted line, and this other vertical asymptote is x equals 1. Notice that as x gets closer and closer to minus 1 from the left, the graph is approaching minus infinity. As x gets closer and closer to minus 1 from the right, the graph is approaching positive infinity. As x gets closer and closer to positive 1 from the left, the graph is approaching minus infinity. And as x gets closer and closer to positive 1 from the right, the graph is approaching positive infinity. Here there is a horizontal asymptote of the x-axis, whose equation again is y equals 0. Notice that f of x is approaching 0 as x approaches infinity, and f of x is also approaching 0 as x approaches minus infinity. The graph on the right points out another interesting aspect of this topic. A function will never cross a vertical asymptote. It just gets closer and closer to the vertical line. But a function can cross a horizontal asymptote in the middle of the graph. It just doesn't cross the horizontal asymptote as x approaches infinity or as x approaches minus infinity. Vertical and horizontal and slant or oblique asymptotes can be found by the following rules. If f of x is a rational function, so it has a polynomial numerator n of x with degree n and a polynomial denominator of degree m, then we can say that we find our asymptotes by these rules. Let's assume that the numerator and denominator have no common factors. If that is the case, then the graph of f will have vertical asymptotes at the zeros of the denominator. What about horizontal asymptotes? There are three rules to determine if a rational function has a horizontal asymptote, and if so, what that is. If the degree of the numerator is less than the degree of the denominator, the graph of f has the line y equals 0, or the x-axis, as a horizontal asymptote. If the degree of the numerator equals the degree of the denominator, the graph of f has the line y equals a sub n over b sub m, the ratio of the leading coefficients, as a horizontal asymptote. If the degree of the numerator is greater than the degree of the denominator, then the graph of f has no horizontal asymptotes. What about slant or oblique asymptotes? If the degree of the numerator is exactly one more than the degree of the denominator, then you are going to have a slant asymptote. Here's how you find it. Use polynomial long division to divide the numerator by the denominator. That will give you a linear quotient and a remainder. Ignore the remainder and set y equal to the quotient, and that will be the equation of a slant asymptote of the function. Now, the rules which we have just talked about are assuming that the numerator and denominator have no common factors. What happens if they do? If x minus k is a common factor of the numerator and denominator, then the graph of the function will have a hole, not a vertical asymptote, at a point whose x-coordinate is k. How do you graph a rational function? In the first place, you want to simplify f, if possible, by canceling out any common factors of the numerator and denominator. Remember that the zeros of the common factors give rise to holes in the graph. Now that you have your rational function in simplified form with no more common factors, find and plot the y-intercept by evaluating f of 0. Substitute a 0 for the x and calculate the y value. Find the real zeros of the numerator, if there are any, by solving the equation where you set the numerator equal to 0 and then plot those corresponding x-intercepts. Now find the real zeros of the denominator by setting the denominator equal to 0. Those will be the locations of vertical asymptotes. Find and sketch any horizontal or any slant asymptote by the rules we just discussed. Plot at least one point between and one point beyond each x-intercept and each vertical asymptote. And then connect your graph with smooth curves between and beyond those vertical asymptotes. Let's look at some examples. Suppose you were asked to graph h of x equals x squared minus 5x plus 4 over x squared minus 4. The degree of the numerator is 2, and the degree of the denominator is 2. That tells me that I have a horizontal asymptote at the ratio of the lead coefficients. In this problem, it's 1 over 1. 1 divided by 1 is just 1. So y equals 1 would be the equation of a horizontal asymptote. It turns out, as x approaches minus infinity, the y, or h of x, is going to approach 1 from above. And as x approaches positive infinity, the y, or h of x, is going to approach 1 from below. The red curves here are the graph of h of x. Notice that as x is approaching positive infinity, the graph is getting closer to 1 from below. As x approaches minus infinity, the graph is getting closer and closer to 1 from above. The blue dotted line here, this horizontal line, is the horizontal asymptote y equals 1. If I substitute a 0 for x into my function, I'm going to have h of 0 is 4 over minus 4, which is minus 1. So the y-intercept is at 0 minus 1 here, this point. Also, I can factor my numerator, x minus 1 times x minus 4, over x plus 2 times x minus 2. There are no factors that cancel out, so there are no holes in this graph. The x-intercepts occur at the zeros of the numerator, which would be 1 and 4. So the x-intercepts are 1, 0, and 4, 0. Here is the point 1, 0. Here is the point 4, 0. How about vertical asymptotes? Those occur at the zeros of the denominator here. So I will have a vertical asymptote at x equals -2 and a vertical asymptote at x equals 2. Those are these two vertical dashed lines. And you will notice as x approaches -2 from the left, the function is approaching positive infinity. As x gets closer and closer to -2 from the left, the function is going up toward positive infinity. As x approaches -2 from the right, the function is getting closer to minus infinity. So as x approaches -2 from the right, the function is going toward minus infinity. The other asymptote, x equals 2, you can notice from the graph as x approaches 2 from the left, the function is approaching infinity. As x is approaching 2 from the left, the function is going up toward positive infinity. As x approaches 2 from the right, the function is approaching minus infinity. So as x gets closer and closer to 2 from the right, the function is approaching minus infinity. And you can see the graph there, the red curves. How did I know that this branch of the graph was on this side of my horizontal asymptote rather than below? You can check by just substituting a value of x along here, say -7, into the function and plotting the corresponding point. -7, it turns out if you substitute a -7 for x into the function h, you come out with a y value that's just slightly less than 2, a point here that is above this horizontal asymptote. So I know this part of the curve is along this line. Let's look at another example. Suppose you are supposed to graph g of x is x plus 2 over x squared plus 6x plus 8. I can factor that denominator as x plus 4 times x plus 2. The x plus 2 in the numerator and denominator is a common factor. When that is canceled out, it equals 1 over x plus 4 for all values of x not equal to -2. At -2, the original function g is undefined because it would give me a 0 in the denominator. The function 1 over x plus 4 is defined at -2, but my original function, which I'm trying to graph, is undefined at -2. Since this was a factor that canceled out, that gives rise to a hole in the graph when x is -2. Where did I get this y coordinate of 1/2? I simply substitute the -2 into the expression after the common factor has been canceled out. So if x is -2, I have 1 over -2 plus 4, that is 1/2. I'm going to have a hole in my graph at the point -2, 1/2. If you look at the graph, this is a little hollow dot. This represents the hole at the point -2, 1/2. Now, if I'm looking at 1 over x plus 4, I can tell that there is no x-intercept because there are no zeros of the numerator. The y-intercept would be 0, 1/4. If x is 0, y is 1/4. So 0, 1/4 is going to be the y-intercept here. I have a vertical asymptote at x equals -4, and as x approaches -4 from the left, g of x approaches minus infinity. As x approaches -4 from the right, g of x approaches infinity. You can see that on the graph here. The vertical dashed line is x equals -4. That's my vertical asymptote. As x is approaching -4 from the left, the function is going toward minus infinity. As x approaches -4 from the right, the function is going toward positive infinity. the degree of the numerator is less than the degree of the denominator. So there is a horizontal asymptote at y equals 0. In other words, the x-axis is my horizontal asymptote. As x approaches minus infinity, g of x is approaching 0 from below over here. And as x approaches infinity, g of x is approaching 0 from above. So I have these two branches of the graph of g of x. Here's another example. Let's say f of x is x squared plus x plus 1 over x. X squared over x is just x. X over x is 1. And then plus 1 over x would be an equivalent algebraic way of expressing this function. Here, the degree of the numerator is 2, the degree of the denominator is 1. Since the degree of the numerator is exactly 1 more than the degree of the denominator, I will have a slant or oblique asymptote, but not a horizontal asymptote. The equation of the slant asymptote would just be y equals x plus 1, the quotient that you get when you divide the numerator by the denominator. I think you can intuitively understand why that would be true. As x approaches infinity or minus infinity, 1 over x is approaching 0, so the f of x, or the y value, is just going to be closer and closer to x plus 1. Here, the slanted blue dotted line is the slant asymptote, the graph of y equals x plus 1. There is a vertical asymptote at the 0 of the denominator. So x equals 0 is going to be my vertical asymptote. That's the same thing as the y-axis. As x approaches 0 from the left, the function approaches minus infinity. As x approaches 0 from the right, the function approaches infinity. So as x gets closer to 0 from the left, the function is going toward minus infinity. As x approaches 0 from the right, the function is going toward infinity. There's no x-intercept because there are no real zeros of this numerator. There is no y-intercept. X can never be 0 for this function. So the red branches of the graph that you see here would be the graph of f of x. This is the point 1, 3, and the point -1, -1 on these two branches. And you can see how the graph is between the slant asymptote and the vertical asymptote for both branches of the graph. Hopefully you now understand the concept of asymptotes, and they are a tremendous help when you are trying to graph rational functions.